Welcome back to another journey through the cosmos with Science Lullaby. Tonight we're going to explore one of the most captivating questions that has ever emerged from the intersection of physics, philosophy, and human imagination. It's a question that sounds like pure science fiction, yet it arises naturally from some of our most successful scientific theories. The question is deceptively simple. Do parallel universes really exist? This isn't just idle speculation or the stuff of comic books and fantasy novels. This is a question that serious physicists, cosmologists, and theoretical scientists grapple with using mathematics, observations, and carefully constructed logical arguments. It's a question that touches the very nature of reality itself, asking us to consider whether everything we can see, everything we've ever known, might be just one small part of something vastly larger and more complex than we ever imagined. So settle in, get comfortable, and let us wander together through this landscape of possibility. We'll explore the science, examine the theories, weigh the evidence, and consider what it all might mean. Whether parallel universes exist or not, the journey of exploring the question reveals something profound about how far human understanding has come, and how much mystery still remains in the fabric of existence itself. There's something deeply human about wondering what lies beyond the edges of what we can see and know. Throughout history, we've always been drawn to the boundaries of our understanding, always curious about what might exist just past the horizon of perception. Ancient peoples wondered what lay beyond the visible stars, what might exist past the edge of their known world. Medieval sailors imagined what continents might float in unexplored oceans. And now, with our modern scientific understanding, we find ourselves asking an even more extraordinary question. Might there be entire universes existing alongside our own, forever hidden from our view? The very concept seems to challenge our most basic assumptions about reality. We tend to think of the universe as everything that exists, all of space, all of time, all of matter and energy. The word itself comes from Latin roots meaning turned into one, a single unified whole. Yet modern physics has led some of the brightest minds in science to seriously consider that our universe might not be alone, that it might be just one bubble floating in an infinite foam of other universes, each with its own laws of physics, its own history, its own unique character. This isn't a new question exactly. Philosophers have pondered the possibility of multiple worlds for centuries. In ancient times, Greek atomists like Democritus speculated about infinite worlds arising from the random collision of atoms. In the 16th century, the philosopher Giordano Bruno proposed that the universe contained an infinite number of inhabited worlds. But what makes our modern consideration of parallel universes different is that it doesn't arise from pure philosophical speculation. Instead, it emerges naturally from our best scientific theories about how reality works. When physicists and cosmologists talk about parallel universes today, they're not engaging in flights of fancy. They're following the mathematics where it leads them, taking seriously what their equations seem to be telling them about the nature of existence. This makes the question both more exciting and more unsettling. If parallel universes are real, they're not just interesting philosophical possibilities. They would be actual physical things as real as the chair you're sitting in or the air you breathe, just forever beyond our reach. The implications of such a reality would be staggering. If parallel universes exist, there might be versions of reality where the dinosaurs never went extinct, where you made different choices at crucial moments in your life, where the fundamental laws of physics operate in an entirely different way. There might be universes where stars never formed, where matter never coalesced into galaxies, where the constants of nature are tuned so differently that nothing remotely resembling life could ever arise. And somewhere in that infinite collection of possibilities, there might be universes almost identical to ours, differing in only the tiniest details. This touches something profound in the human psyche. We've always been fascinated by the road not taken, by alternate possibilities, by the question of what might have been. Literature and art have explored these themes for as long as humans have been telling stories. But parallel universes take this fascination and ground it in mathematical physics, suggesting that all those alternate possibilities might not just be imaginary, they might be real, existing somewhere beyond the boundaries of our observable cosmos. Yet this very grandiosity is also what makes many scientists uncomfortable with multiverse theory. Some argue that if we can't observe these other universes, if they're forever beyond the reach of any possible experiment or measurement, then talking about them isn't really science at all, it's metaphysics dressed up in mathematical clothing. Others counter that we routinely accept the existence of things we can't directly observe, as long as their existence is implied by theories that make successful predictions about things we can observe. Black holes, for instance, were accepted as real long before we had direct observational evidence of them, because general relativity predicted their existence, and general relativity had proven itself right about so many other things. The debate about parallel universes thus becomes a debate about the nature of science itself. What counts as legitimate scientific theorizing? How do we distinguish between a scientific hypothesis and mere speculation? Can something be scientifically meaningful even if it's impossible to test directly? These are not easy questions, and thoughtful scientists disagree about the answers. What's clear is that the question of parallel universes isn't going away. Multiple independent lines of reasoning in modern physics all seem to point toward the possibility of a multiverse. Quantum mechanics, cosmic inflation, string theory. Each of these well-established or seriously considered frameworks leads naturally to scenarios involving multiple universes. This convergence is striking. It suggests that even if we're wrong about the details, we might be onto something real, something fundamental about how reality is structured at its deepest level. As we explore these ideas tonight, we'll encounter concepts that can seem strange, counterintuitive, even impossible. But remember that our intuitions are shaped by our everyday experience of medium-sized objects moving at medium speeds in familiar environments. The universe under a microscope looks nothing like the world of our daily experience. The universe at cosmic scales operates according to principles that would seem utterly alien to someone who had never studied physics. So when we encounter ideas that seem bizarre or unbelievable, it's worth remembering that reality itself has already proven to be far stranger than common sense would suggest. The question of parallel universes sits at the frontier of human knowledge, at that exciting and uncertain boundary where established science begins to shade into speculation, where mathematics points toward possibilities that may forever remain beyond direct observation, where our theories become so successful that they start making predictions that seem to transcend the limits of the empirically testable. It's a strange and wonderful place to be, full of both profound insights and humbling uncertainty.
To understand one of the most compelling arguments for parallel universes, we need to journey into the bizarre realm of quantum mechanics, the physics of the very small, where atoms and electrons and photons operate. according to rules that seem to bear no resemblance to the familiar world of everyday experience. Quantum mechanics emerged in the early 20th century as physicists struggled to understand the behavior of matter and energy at atomic scales. What they discovered was deeply unsettling. At these tiny scales, particles don't behave like miniature versions of familiar objects. They behave in ways that seem fundamentally weird, displaying properties that challenge our most basic intuitions about how reality works. One of the central mysteries of quantum mechanics involves something called superposition. In the quantum world, a particle can seemingly exist in multiple states simultaneously. An electron, for instance, can be in a superposition of being in two places at once, or spinning in two directions at the same time, or having two different energies simultaneously. This isn't just about our ignorance of where the electron actually is. According to the mathematics of quantum mechanics, the electron genuinely exists in this strange multiple state until something disturbs it and forces it to choose one state or the other. This leads to what's called the measurement problem, one of the deepest puzzles in all of physics. When we actually look at a quantum particle, when we measure it, we always find it in one definite state. The electron is here or there, spinning this way or that way, having this energy or that energy, never both. So what happens to make the particle go from existing in multiple states to existing in just one? When does a quantum system stop being in superposition and start being definite? Where's the boundary between the quantum world of multiple simultaneous possibilities and the classical world of single definite outcomes? The traditional answer, developed in the 1920s and 30 years primarily in Copenhagen, where Niels Bohr worked, suggests that the act of measurement itself causes what's called the collapse of the wave function. The wave function is a mathematical object that describes all the possible states a quantum system might be in. According to the Copenhagen interpretation, when we measure a quantum system, its wave function suddenly collapses, randomly selecting one of the possible outcomes to become real while all the others disappear. But this answer raises more questions than it resolves. What counts as a measurement? Does it require a conscious observer? At what point does the collapse happen? The mathematics of quantum mechanics describes a smooth, deterministic evolution of the wave function over time. But collapse introduces a sudden random discontinuity that doesn't fit naturally into the equation. It feels like something added on to make the theory match what we observe, rather than emerging naturally from the theory's fundamental principles. In 1957, a graduate student at Princeton named Hugh Everett proposed a radically different solution to the measurement problem. Everett suggested that we take the mathematics of quantum mechanics completely seriously and stop adding in this mysterious collapse process. According to his interpretation, the wave function never collapses. It just keeps evolving smoothly and deterministically, exactly as the equations describe. When a measurement happens, the wave function doesn't collapse to one outcome. Instead, it evolves into a superposition that includes the measuring device, the observer, and everything they interact with. The consequence of this idea is extraordinary. If the wave function never collapses, then all the possible outcomes of a quantum measurement actually happen. They don't happen in the same place though. Instead, reality splits into multiple branches, each one containing a different outcome. In one branch, the electron went left. In another branch, it went right. In one branch, you measured the particle's spin as up. In another branch, you measured it as down. Each version of you experiences only one outcome and sees only one definite result. but all the versions exist with equal reality in what Everett called the universal wave function. This is the many worlds interpretation of quantum mechanics, though Everett himself preferred to call it the relative state formulation. It proposes that quantum mechanics describes not one universe but an unimaginably vast collection of parallel universes, constantly splitting and branching with every quantum event, and quantum events happen all the time, everywhere, at microscopic scales throughout the cosmos. Every radioactive decay, every photon absorption, every collision between particles, all of these create new branches in the universal wave function, new parallel realities diverging from each other. At first glance, this seems like an absurdly extravagant solution to the measurement problem. To avoid adding one extra postulate to our theory, the collapse of the wave function, we instead postulate the existence of countless parallel universes. How could this possibly be considered a simpler or more elegant approach? But proponents of many worlds argue that it actually is simpler in a deep sense. The Everett interpretation takes the fundamental equations of quantum mechanics and applies them consistently to everything, without exception. There's no arbitrary boundary between the quantum world and the classical world, no mysterious moment when wave functions suddenly collapse, no special role for observers or measuring devices. Everything is quantum. Everything evolves according to the same beautiful deterministic equations, and the appearance of definite outcomes emerges naturally from the mathematics without needing to add anything extra. The parallel universes in the many worlds interpretation are not separate bubbles floating in some higher dimensional space. They all exist in the same space, the same time, occupying the same points. What separates them is something called decoherence, when quantum systems interact with their environment, and in practice, everything is constantly interacting with its environment. The different branches of the wave function become effectively isolated from each other. They can't interfere or interact anymore. Each branch becomes, for all practical purposes, a separate universe, even though mathematically they're all part of one universal wave function. Think of it like this. Imagine you're watching a river split around an island. Downstream from the island, you have two separate streams of water, each following its own path, each having its own distinct flow and character. But they're still part of the same river system, still connected if you zoom out far enough. The branches of the many worlds are something like that, separate in terms of what we can experience and observe, but unified at a deeper mathematical level. One of the most famous thought experiments in quantum mechanics illustrates these ideas vividly. It's called Schrödinger's cat, proposed by physicist Erwin Schrödinger in 1935 as a way of highlighting how strange quantum mechanics becomes when applied to everyday objects. Imagine a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. The atom has a 50% chance of decaying within 1 hour. If it decays, the Geiger counter detects it and triggers a mechanism that breaks the vial, releasing the poison and killing the cat. If it doesn't decay, the cat lives. According to quantum mechanics, before we open the box, the radioactive atom exists in a superposition of decayed and not decayed. And if quantum mechanics really describes everything, then the entire system, atom, Geiger counter, poison vial, and cat, must also exist in a superposition. The cat is both alive and dead until we open the box and observe what happened. This seemed absurd to Schrödinger, which was precisely his point. He was trying to show how weird it was to apply quantum mechanics to everyday objects. But in the many worlds interpretation, this scenario isn't absurd at all. It's exactly what we should expect. When the hour is up, the universal wave function has branched into two. In one branch, the atom decayed,
The poison was released, and the cat died. In the other branch, the atom didn't decay, and the cat survived. Both outcomes are real, existing in separate branches of reality. When you open the box, you don't cause the cat to become either dead or alive, you just find out which branch you're in. Critics of the many worlds interpretation raise several concerns. One involves probability. In ordinary quantum mechanics, we can predict that certain outcomes are more likely than others. An electron might have a 70% chance of going left and a 30% chance of going right. But if both outcomes actually happen in different branches, where does probability come from? If everything possible happens, what does it even mean to say that one outcome is more likely than another? Defenders of many worlds have developed sophisticated answers to this question, involving the relative thickness or weight of different branches, and how we should think about our own existence, spread across multiple branches. It's a subtle and complex discussion, one that gets into deep questions about probability, identity, and what it means to ask about the likelihood of our own experience.
Another concern is simpler but perhaps more fundamental. Many worlds seems to violate Occam's razor, the principle that we shouldn't multiply entities beyond necessity. If we have two theories that explain the same observations equally well, we should prefer the simpler one, the one that requires fewer assumptions about what exists. And surely a single universe is simpler than an infinite number of parallel universes, right? But again, proponents argue that this gets the simplicity comparison backwards. The many worlds interpretation actually requires fewer fundamental assumptions than the Copenhagen interpretation. It doesn't need to assume that wave functions collapse, doesn't need to define what counts as a measurement, doesn't need to specify where the boundary is between quantum and classical. It just has the wave function and its equation of motion. The parallel universes aren't extra assumptions piled on top. They're consequences that emerge naturally when you take the basic equations seriously. Physicist David Deutsch has argued that other interpretations of quantum mechanics are actually talking about parallel universes too. They just don't admit it. When the Copenhagen interpretation says that unmeasured particles exist in superposition, where does that superposition exist? When an experiment shows that a photon somehow went through two slits at once, what does that mean physically? Deutsch suggests that the interference patterns we observe in quantum experiments are best understood as showing us shadows cast by parallel universes, glimpses of other branches of reality interacting with our own before decoherence separates them completely. Whether or not you find the many worlds interpretation convincing, it represents one of the most radical and philosophically profound ideas to emerge from 20th century physics. It suggests that the reason quantum mechanics seems so strange might not be because nature is fundamentally indeterministic or observer-dependent, but because reality is far vaster than we ever imagined. So vast that it contains every possible outcome of every quantum event, all existing simultaneously in an endlessly branching tree of parallel universes. And here's something remarkable to consider. If the many worlds interpretation is correct, then parallel universes aren't some exotic possibility that might exist somewhere far away. They're right here occupying the same space as our universe, separated from us not by distance but by the quantum branches of the wave function. Every moment with every quantum event in your brain, in your body, in the world around you, reality is branching. Countless versions of you are experiencing countless variations of this moment, each one thinking they're the only version, each one feeling exactly as real and solid and definite as you feel right now.
It's a dizzying thought, but that's quantum mechanics for you. It takes our intuitions about reality and turns them inside out, revealing possibilities so strange that they feel more like metaphysics than physics. Yet these aren't idle speculation. They arise directly from trying to understand what the mathematics of one of our most successful scientific theories is telling us about the nature of the world. While quantum mechanics offers one path to parallel universes through the mathematics of wave functions and superposition, cosmology, the study of the universe as a whole, offers a completely different route to the same strange conclusion. This path begins with a mystery about the earliest moments after the Big Bang and leads to a scenario of eternal inflation spawning endless bubble universes in an ever-expanding cosmic foam. Let me take you back to the 1970s and early 80s when cosmologists were developing their understanding of the universe's history. They had good reason to think that the universe began in an extremely hot, dense state roughly 14 billion years ago, and had been expanding ever since. But several puzzles remain. Why was the universe so uniform on large scales, with the cosmic microwave background radiation showing almost exactly the same temperature in every direction? Different regions of the observable universe are so far apart that light hasn't had time to travel between them since the Big Bang. So how did they all end up at the same temperature? This is called the horizon problem, and it seemed to require an explanation. How could regions of space that had never been in contact with each other look so similar? Another puzzle involved the overall geometry of the universe. Observations suggested that space was very close to being perfectly flat, neither curved like the surface of a sphere, nor curved like a sat, but in standard Big Bang cosmology, a flat universe represents an incredibly delicate balance that seems far too special to occur by chance. In the early 1980s, several physicists independently proposed a solution: cosmic inflation. The idea was that in the first tiny fraction of a second after the Big Bang, we're talking about a period lasting perhaps 10 to the negative 35 seconds after the universe began, space itself underwent a period of extraordinarily rapid expansion. During this inflationary epoch, the universe expanded by a factor of at least 10 to the 26th, possibly far more, in an incomprehensibly short time. This rapid expansion would solve both the horizon problem and the flatness problem. Before inflation, all the parts of what would become our observable universe were close enough together to have reached the same temperature. Inflation then stretched them apart so quickly that they've been out of contact ever since, and any initial curvature of space would have been stretched flat by inflation, just as inflating a balloon makes its surface appear flatter and flat. The mechanism driving inflation is thought to be a quantum field called the inflaton field, which filled all of space with a peculiar form of energy. This inflationary energy had an unusual property. It created a kind of anti-gravity, a repulsive effect that caused space to expand exponentially. As the inflaton field gradually decreased in energy, the inflationary period came to an end, and the energy that had been stored in the field was converted into ordinary matter and radiation, reheating the universe and setting the stage for the more sedate expansion that has continued ever since. Cosmic inflation quickly became an extremely successful theory. It elegantly solved several problems with the standard Big Bang model, and it made predictions that were later confirmed by precise observations of the cosmic microwave background. The pattern of tiny temperature fluctuations in that background radiation matches what inflation theory predicts with remarkable accuracy. By the early 21st century, inflation had become the standard paradigm for understanding the universe's earliest moments.
But there was a twist. As physicists studied inflation more carefully, they realized that the theory has an almost inevitable consequence. It probably doesn't end everywhere at once. This insight emerged from understanding how quantum fluctuations interact with the inflation. Even as the average value of the inflation field decreases, causing inflation to end in some regions, quantum fluctuations can cause it to increase in other regions, prolonging inflation. And because inflation causes space to expand exponentially, regions that are still inflating quickly dominate the volume of the universe, even as other regions stop inflating and form normal matter and radiation. This leads to a scenario called eternal inflation. Picture it like this. The universe starts inflating. In some regions, inflation ends, and a bubble universe forms, a pocket of normal space filled with matter and energy, where galaxies and stars and planets can eventually form. Our observable universe is one such bubble. But outside our bubble, inflation continues, and in that still inflating region, more bubbles form, each one becoming its own universe, with its own Big Bang. Meanwhile, the inflating region keeps getting bigger, creating more and more space for yet more bubbles to form. This process never stops. The inflating region grows faster than bubbles form within it, so there's always room for more. You end up with an eternally inflating background, giving birth to an infinite number of bubble universes, each separated from the others by regions of space that are still inflated. Each bubble is causally disconnected from all the others. Light can't travel from one bubble to another, because the intervening space is expanding too fast. Each bubble universe is, in a very real sense, its own universe, with its own Big Bang, its own history, its own physical evolution. Now, here's where things get really interesting. The properties of each bubble universe might not be the same. In theories that combine inflation with ideas from particle physics, particularly string theory, the inflation field can settle into different minimum energy states in different bubbles, and these different vacuum states correspond to different physical laws. The fundamental constants of nature, things like the strength of gravity, the mass of the electron, the speed of light, might have different values in different bubble universes. The forces that govern how particles interact might work differently. The very fabric of physical law might vary from one bubble to the next. This idea of a multiverse with varying physical laws addresses one of the deepest mysteries in physics: fine-tuning. Our universe appears to be exquisitely calibrated for the emergence of complex structures and life. The fundamental constants have values that fall within an incredibly narrow range that allows stars to form, atoms to be stable, chemistry to work, and life to evolve. Change almost any of these constants by even a small percentage, and you get a universe where nothing interesting happens. Maybe stars never form, or they burn out too quickly, or atoms fall apart, or nuclear reactions can't happen. This fine-tuning has puzzled physicists for decades. Why should the constants of nature have such precisely calibrated values? It seems almost impossibly lucky. Some have argued that this points to a cosmic designer who set the constants to allow for life. Others have suggested that there must be some deeper theory we haven't discovered yet, one that explains why the constants have to have the values they do. But eternal inflation offers a different answer. Maybe the constants aren't special. Maybe there are countless bubble universes out there with every possible combination of fundamental constants, and we find ourselves in one of the rare bubbles where the constants happen to allow for life, simply because those are the only bubbles where anyone can exist to wonder about the question. This is an application of what's called the anthropic principle,
The observation that the universe must be compatible with the existence of observers, otherwise there wouldn't be anyone here to observe it. In a vast multiverse spawned by eternal inflation, the fine-tuning of our universe isn't mysterious at all. It's just selection bias. We necessarily find ourselves in a bubble universe with the right conditions for life, not because our bubble is special, but because we couldn't exist in the vast majority of bubbles where the conditions are hostile to life. It's like marveling at how lucky we are to live on a planet with breathable air and liquid water. It's not luck, it's just that we couldn't have evolved anywhere else. This anthropic explanation is controversial. Some physicists find it deeply unsatisfying, arguing that it gives up on actually explaining why the constants have the values they do and instead just appeals to vast numbers of possibility. Others counter that this might simply be how reality is. Perhaps there isn't a deeper explanation. Perhaps the apparent fine-tuning is genuine coincidence, made unsurprising by the existence of countless other universes.
The bubble universe scenario also raises intriguing questions about what could happen if two bubbles collided. In principle, if two expanding bubbles ran into each other, the collision might leave detectable traces. In the cosmic microwave background radiation, which is like a baby picture of our universe taken when it was just 380,000 years old, a bubble collision might show up as a circular pattern of temperature variations. Physicists have actually searched for such patterns in high-precision maps of the microwave background. So far, no convincing evidence of bubble collisions has been found. The patterns we see in the cosmic microwave background can be explained by simpler processes that occurred entirely within our own bubble universe. But the absence of evidence isn't evidence of absence, and the search continues. If we did find evidence of a bubble collision, it would be one of the most profound discoveries in the history of science. Direct proof that our universe is not alone, that other universes exist beyond the horizon of what we can normally see. The eternal inflation multiverse is in some ways more tangible and physical than the many worlds quantum multiverse. The bubble universes exist in actual space, albeit space that's so far away and expanding so fast that we can never reach it. They're made of the same kinds of stuff as our universe: energy, matter, space-time. They're just separated from us by insurmountable cosmic distances. Yet in another sense, the bubble multiverse is more speculative. While eternal inflation follows naturally from our best understanding of the universe's early moments, we can't directly observe it happening. We can't see other bubbles forming or measure the properties of the inflating background that spawned. We have to infer their existence from the mathematics of inflation theory and our observations of the cosmic microwave background. Physicist Alan Guth, one of the pioneers of inflation theory, has described the multiverse arising from eternal inflation as the ultimate free lunch. The idea is that you don't need huge amounts of energy or special initial conditions to create a universe. A tiny patch of space in the right kind of vacuum state can inflate into an enormous universe, and the energy needed for all the matter and radiation in that universe gets borrowed from the gravitational field. The total energy of a closed universe, including both the positive energy in matter and radiation, and the negative energy in gravity, adds up to zero. So creating a universe doesn't actually cost anything in terms of energy. Nature can spawn universes freely, endlessly, without violating any conservation laws. It's a spectacular vision, an infinite ocean of eternally inflating space, constantly giving birth to new bubble universes, each one a cosmos unto itself, with its own Big Bang and its own evolution. Some bubbles might be similar to ours, others might be radically different, with different numbers of dimensions, different particles, different forces. The variety would be limitless, constrained only by what the underlying laws of physics allow. And somewhere in that vast multiverse, if this picture is correct, is our bubble, the universe we call home, the only one we can ever observe or visit, or know directly. It's both humbling and exhilarating to contemplate. Humbling because it makes our universe, already incomprehensibly vast, into just one small part of an even vaster reality. Exhilarating because it reveals that the cosmos might be far richer, far more varied, far more creative in its possibilities than we ever imagined. Whether this picture is correct remains to be seen. The evidence for cosmic inflation is strong, but the step from inflation to eternal inflation involves extrapolating our theories into realms we can't directly observe. Still, the fact that this scenario emerges so naturally from well-established physics makes it impossible to dismiss as mere speculation. It's a serious scientific hypothesis about the nature of reality at its largest scales, one that forces us to reconsider what we mean when we talk about the universe and our place within it. Our journey through parallel universe theories now takes us into perhaps the most mathematically complex and conceptually challenging territory: string theory and its associated landscape of possible universe. This is where theoretical physics becomes almost dreamlike in its abstraction, dealing with dimensions we can't perceive and possibilities that stretch our imagination to its limit. String theory emerged in the late 20th century as an attempt to reconcile two of our most successful but seemingly incompatible theories: quantum mechanics, which governs the behavior of the very small, and general relativity, which describes gravity and the large-scale structure of space-time. These two theories work wonderfully within their own domains, but when you try to combine them, when you need to describe situations involving both quantum effects and strong gravity, like the interior of a black hole, or the first moments of the Big Bang, they produce nonsensical results, infinities that can't be removed through normal mathematical techniques. String theory proposes a radical solution. Maybe the most fundamental constituents of reality aren't point-like particles, but tiny vibrating strings of energy. These strings are unimaginably small, roughly 10 to the negative 35 meters in length, far below anything we could ever hope to observe directly. Different vibration patterns of these strings correspond to different particles. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is yet another vibration pattern. This simple-sounding idea turns out to have profound implications. When physicists work out the mathematics of vibrating strings, they find that string theory naturally incorporates both quantum mechanics and gravity. The theory is, in principle, a unified framework that could describe all the forces and particles in nature. It's what physicists call a theory of everything, though whether it actually succeeds in being one remains hotly debated. But string theory comes with a price. It requires extra dimensions of space. The mathematics only works consistently if space is not 3 dimensions, but 10 dimensions, or in some versions of the theory, 11. Where are these extra dimensions? The standard answer is that they're curled up so small that we can't detect them. Imagine walking along a tightrope. From a distance, the rope looks one-dimensional, like a line. But if you were an ant walking on the rope, you'd notice that the rope actually has a tiny circular dimension as well. You could walk around the circumference of the rope at any point. The extra dimensions in string theory are supposed to be curled up like this, but on such an incredibly small scale that they're invisible to us.
Here's where the multiverse enters the picture. The way these extra dimensions are curled up determines the physics we observe in the three large dimensions we experience. Different configurations of the compact dimensions lead to different physical laws, different particles, different force. It's like how the shape and size of a guitar string determines what note it plays. The geometry of the extra dimensions determines what physics plays out in our observable universe. And it turns out there are many possible ways to curl up the extra dimension. The shapes that work are called Calabi-Yau manifolds, beautiful and complex mathematical objects that exist in six-dimensional space. Physicists have identified thousands of different Calabi-Yau manifolds, and when you include additional complications like magnetic fields threading through these shapes, the number of possible configurations explode. Estimates suggest there might be 10 to the power of 500 or more different possible vacuum states in string theory, each corresponding to a different universe, with different physical laws. This vast collection of possibilities is called the string theory landscape. Think of it as a cosmic terrain with countless valleys and peaks. Each valley represents a stable or semi-stable vacuum state, a possible universe with its own particular physics. Our universe corresponds to one of these valleys, but there's no obvious reason why nature should have chosen our valley rather than any of the countless others. For many years, string theorists hoped to find some principle that would select out a unique solution, a single valley in the landscape that was somehow special or inevitable. But as understanding of string theory deepened, this hope faded. The landscape appeared to be genuinely vast and varied, with no mechanism for selecting one solution over another. This led some physicists, notably Leonard Susskind at Stanford, to propose a radical idea. Maybe all those solutions are real. Maybe each valley in the string landscape corresponds to an actual universe existing somewhere in the multiverse. Combined with eternal inflation, you get a picture where different bubble universes don't just have different initial conditions or randomly varying constants. They actually correspond to different solutions in the string landscape, different ways of curling up the extra dimension, genuinely different physics at the most fundamental level. This string landscape multiverse would be incomprehensibly diverse. In some universes there might be more or fewer kinds of fundamental particles. The forces might have completely different strengths, or even different numbers of dimensions where they operate. Space-time itself might be structured differently. Some universes in the landscape might be completely inhospitable to any kind of structure or complexity. Others might be capable of supporting life, though perhaps based on entirely different chemistry and physics than what we know. The landscape provides a potential explanation for the fine-tuning problem that we encountered earlier. Why do the constants of nature in our universe seem so precisely calibrated? If there are 10 to the 500 possible universes in the landscape, each with different constants, then it's not surprising that at least one of them would have constants suitable for life. We find ourselves in that one because we couldn't exist anywhere else. The anthropic principle strikes again, now applied to the full diversity of the string landscape. This application of the anthropic principle is controversial within the physics community. Pioneers like Nobel laureate David Gross have argued that relying on anthropic reasoning represents a kind of giving up, accepting that we can't predict or explain why the universe has the properties it does, and instead just saying it's one of many possibilities that happens to allow observers. Others, including Susskind, counter that we should follow the science wherever it leads, and if string theory genuinely predicts a vast landscape of possibilities, then we need to take that prediction seriously, even if it seems philosophically unsatisfying.
There's also a deeper question about whether the landscape is even a scientific idea in the traditional sense. Science normally works by making predictions that can be tested through observation or experiment. But if the other universes in the landscape are forever inaccessible to us, separated by the vast distances of eternal inflation or existing in fundamentally different vacuum states that we could never visit, then how can we test the theory? How do we distinguish it from mere speculation? Defenders of the landscape point out that even if we can't observe other universes directly, the landscape might still make testable predictions about our own universe. If our universe is a randomly chosen valley in the landscape, then its properties should be typical of universes capable of supporting life. We might be able to predict things about our universe based on what would be common or likely across the landscape. Some physicists have attempted to make such statistical predictions, though this requires making assumptions about how count universes in the landscape, which is far from straightforward. There's also the possibility that the landscape could be tested indirectly. If string theory is correct, it might make other predictions that we can test in particle accelerators or astronomical observations. If those predictions are confirmed, it would give us confidence in the overall framework of string theory, landscape and all. Conversely, if string theory turns out to be wrong or incomplete, the landscape would go down with it. The string landscape represents a particular vision of the multiverse, one where the diversity comes not from quantum branching or cosmic inflation's bubble universes, but from the fundamental structure of space-time itself, from the myriad ways that extra dimensions can be configured. It's a multiverse of deep geometrical variety, where physics itself can take wildly different forms. Some physicists find this vision elegant and compelling, seeing in the landscape a kind of ultimate Copernican demotion of human significance. We're not at the center of the solar system, not in a special galaxy, not even in a special universe. We're just inhabitants of one random valley in an unimaginably vast landscape of possibility. Others see it as an unfortunate consequence of a theory that, for all its mathematical beauty, may simply not be the right description of reality. What's remarkable is how different lines of thinking in modern physics, quantum mechanics, cosmic inflation, string theory, all seem to point toward some kind of multiverse. The details differ, the mechanisms are different, but the common thread is this: our universe might not be alone. Whether these different multiverse scenarios are describing the same underlying reality from different angles, or whether some are right and others wrong, or whether the whole multiverse idea is a grand mistake remains to be seen. The landscape of string theory, like the other multiverse theories we've explored, sits at that fascinating and uncertain boundary, where our most sophisticated mathematics points toward possibilities that may forever transcend direct observation. It asks us to consider whether elegance and mathematical consistency might guide us to truths about reality that we can never empirically verify in the traditional sense. It's a profound question about the nature of knowledge itself and what it means to understand the cosmos we inhabit. Let me tell you about one of the most puzzling facts in all of cosmology, a mystery that lies at the heart of why so many physicists take the idea of a multiverse seriously. It's called the fine-tuning problem, and it concerns the remarkable precision with which the fundamental constants of nature seem to be calibrated for the existence of complexity and life. To understand this, we need to think about what the universe would be like if its fundamental constants, things like the strength of gravity, the mass of the electron, the charge of the proton, the cosmological constant, were different from their actual value. Not wildly different, mind you, but changed by just a small percentage or even less. What physicists have discovered through detailed calculations is that in most cases, even tiny changes would result in a universe radically different from our own, one where the kinds of structures we depend on, stars, planets, atoms, chemistry, couldn't exist. Let's look at some specific examples. Consider the cosmological constant, which represents a kind of energy density inherent in empty space itself. This constant determines the rate at which the universe expands. The actual value of the cosmological constant is very small but not zero. Small enough that the universe has expanded at a rate that allowed galaxies and stars to form, but fast enough to prevent the universe from recollapsing too quickly. Now here's the thing. Theoretical calculations from particle physics suggest that the cosmological constant should be enormously larger than it actually is, larger by a factor of 10 to the power of 120. That's not a type. Our theoretical predictions are off by 120 orders of magnitude, making this what physicists sometimes call the worst prediction in the history of physics. Yet if the cosmological constant were anywhere close to what theory predicts, the universe would have either recollapsed almost immediately after the Big Bang, or expanded so fast that matter could never have clumped together to form galaxies. Why is the actual value so extraordinarily, exquisitely smaller than what we calculate it should be? We don't know. It's as if nature reached in and carefully dialed down this constant to just the right value, not too big, not too small, but precisely calibrated to allow for a universe with structure and life. It's like finding that the temperature of Earth's atmosphere is precisely controlled to within a fraction of a degree when our calculations suggest it should be millions of degrees hotter or colder. Or consider the strength of the strong nuclear force, which holds atomic nuclei together. If this force were just a few percent weaker, protons and neutrons couldn't bind together to form nuclei. You'd have a universe with only hydrogen, no heavier elements, no carbon, no chemistry, no light. If the strong force were a few percent stronger, nuclear reactions would proceed so efficiently that all the hydrogen in the universe would have fused into heavier elements shortly after the Big Bang. Again, no chemistry, no water, no life. The electromagnetic force shows similar fine-tuning. If it was significantly stronger or weaker, atoms would be unstable or unable to bond into molecules. The ratio of the electromagnetic force to gravity is also critical. Change it by much, and stars either can't form or burn out too quickly to allow time for complex evolution to occur. Even more remarkably, some constants seem fine-tuned in ways that require precise relationships between multiple parameters. Fred Hoyle, the astronomer who coined the term Big Bang, though he favored a different theory, discovered in the 1950s that carbon production in stars depends on a very specific resonance in the carbon nucleus. This resonance has to be at almost exactly the right energy level for carbon to form in stellar cores. A tiny change in the fundamental constants would shift this resonance and make carbon production far less efficient, potentially making carbon-based life impossible. Hoyle, who was not religious and originally skeptical of fine-tuning arguments, found this so striking that he wrote it looked as if someone had monkeyed with the laws of physics to favor the formation of carbon and the subsequent evolution of life. The precision required is astonishing. In some cases, changing fundamental constants by less than 1% would make the universe unrecognizable. This fine-tuning extends to the initial conditions of the universe as well. The density of matter in the early universe, the size and pattern of initial fluctuations, the balance between matter and antimatter, all of these seem to have been set to remarkably precise value. If the initial density had been slightly higher, the universe would have recollapsed before stars could form. Slightly lower, and matter would have dispersed too quickly for gravity to pull it together into structures. Now there are broadly three ways to respond to this apparent fine-tuning. The first is to say that there must be some deeper theory we haven't discovered yet, one that explains why the constants have to have the values they do. Maybe there's a fundamental principle or symmetry that requires these precise relationships. Maybe once we understand physics more deeply, we'll see that the constants couldn't be any different. This is an attractive possibility, and physicists would love to find such a theory. But so far no one has succeeded in developing one that explains all the fine-tuning we observe. The second response is to invoke a cosmic designer. If the constants appear to be precisely tuned for life, maybe that's because they were tuned by some kind of intelligence with the intention of creating a universe suitable for life. This is essentially a modern version of the argument from design, updated for the age of cosmology and particle physics. Some people find this explanation compelling, but it's not a scientific explanation in the usual sense. It doesn't make testable predictions, and it raises its own questions about the nature and origin of the designer. The third response is the multiverse. If there are countless universes with different values of the fundamental constants, then it's not surprising that at least one of them has constants suitable for life. We find ourselves in that one not because it's special or designed, but because we couldn't exist anywhere else. This is the anthropic explanation we've encountered several times already, now applied specifically to the fine-tuning problem. From the anthropic perspective, the apparent fine-tuning isn't actually tuning at all, it's selection bias. Imagine walking into a casino and marveling at how lucky it is that the casino happens to be located in a city with roads and electricity and buildings. That's not luck. Casinos don't get built in inhospitable deserts or on remote mountain tops. They get built where the infrastructure exists to support them. Similarly, observers like us don't evolve in universes where the constants make stars impossible or atoms unstable. We evolve in the tiny fraction of universes where conditions happen to be right. The anthropic explanation is powerful but also unsettling to many physicists. It seems to replace the goal of explaining why things are the way they are with the observation that they couldn't be any other way, given that we're here to ask the question. It feels like giving up on finding a real explanation. Steven Weinberg, a Nobel laureate who has written thoughtfully about fine-tuning, has compared the situation to being dealt a royal flush in poker. Yes, it's incredibly unlikely, but someone has to get some hand, and if you get a royal flush, you shouldn't be that surprised after all. Someone was going to get dealt something. But is that really satisfying? Imagine being dealt a royal flush, not just once, but in every hand you play. At some point you'd start to suspect the deck is rigged, that there's some explanation beyond mere chance. The fine-tuning we observe in our universe isn't just one or two constants being in a narrow range. It's dozens of parameters all falling into the narrow ranges necessary for a complex life-supporting universe. That's a lot of royal flush. The multiverse doesn't entirely solve this problem, it just relocates it. Instead of asking why our universe is fine-tuned, we ask why the multiverse exists, and why it has the particular properties that allow for a vast landscape of different universes. But the multiverse at least provides a framework in which fine-tuning can be understood as selection bias rather than as a cosmic mystery requiring explanation. What's particularly interesting is that different roads in physics all seem to lead to the multiverse, and they do so independent. Quantum mechanics suggests many worlds. Cosmic inflation suggests bubble universes. String theory suggests a landscape of possibilities. And the fine-tuning problem provides motivation for taking all these ideas seriously. These separate lines of evidence don't prove that the multiverse exists.
but they do create a compelling cumulative case that's hard to dismiss entirely. As we contemplate these ideas, we're confronting some of the deepest questions humans can ask. Why does anything exist at all? Why does it have the particular properties it has? Are we here because of pure chance? Because of some kind of selection process operating across a vast multiverse? Or because of some principle or purpose we haven't yet glimpsed? These questions sit at the intersection of physics, philosophy, and perhaps even theology, and the answers, if we can find them, will shape how we understand our place in the cosmos.
With all this talk of parallel universes arising from different areas of physics, you might reasonably ask, what's the actual evidence? Can we see these other universes? Can we detect them somehow? Or is this all just mathematical speculation with no connection to observable reality? The honest answer is that we have no direct evidence for the existence of parallel universes. We can't see them, we can't visit them, and in most multiverse scenarios, the other universes are fundamentally beyond our ability to observe. This raises serious questions about whether the multiverse is even a scientific idea in the traditional sense. However, the situation is more nuanced than it might first appear. While we can't observe parallel universes directly, we can look for indirect evidence, signatures that might reveal their existence even if we can't see the universes themselves. Scientists have proposed several ways this might work, though none has yet produced conclusive results. One of the most concrete searches has been for signs of bubble universe collisions in the cosmic microwave background radiation. As we discussed earlier, if our universe is a bubble in an eternally inflating multiverse, it's possible that we collided with another bubble at some point in our past. Such a collision should leave a distinctive circular pattern in the cosmic microwave background, a disc-shaped region where the temperature and polarization of the radiation looks slightly different from the surrounding sky. Physicists have analyzed the most detailed maps of the cosmic microwave background we have, including data from the Planck satellite, searching for these circular patterns. They've used sophisticated statistical methods to determine whether any features in the data look more like bubble collision signatures than would be expected from random noise. So far, nothing conclusive has emerged. There are some anomalies in the cosmic microwave background, features that don't quite match the simplest theoretical predictions, but none of them clearly point to bubble collisions, and most can be explained in other ways. The lack of bubble collision signatures doesn't rule out the multiverse, though. It could be that our bubble hasn't collided with any others, or that any collisions happened so long ago that the signatures have been washed out or are too subtle to detect. Or it could be that the specifics of how eternal inflation works don't lead to detectable collisions. The absence of evidence isn't quite the same as evidence of absence. Another potential source of evidence relates to the values of the fundamental constants themselves. In a multiverse scenario where different universes have different constants, we might be able to make statistical predictions about what values we should expect to observe. If we assume that our universe is a typical life-supporting universe in the multiverse, then its constants should be fairly common among all life-supporting universes. Steven Weinberg famously made such a prediction about the cosmological constant back in 1987, before it had been measured. Using anthropic reasoning, he argued that the cosmological constant should be small enough to allow galaxies to form, but not so small that it's zero. His prediction gave a range of possible values, and when astronomers finally measured the cosmological constant a decade later by observing distant supernovae, They found that it fell right within Weinberg's predicted range. Some physicists view this as evidence supporting the anthropic multiverse scenario. Others are more skeptical, pointing out that we've only done this exercise successfully once, and even then there are debatable assumptions involved in deriving the prediction. Making and testing anthropic predictions turns out to be quite difficult, in part because it requires making assumptions about what counts as a life-supporting universe, and how to do probability calculations across a multiverse, neither of which is straightforward. For the many worlds interpretation of quantum mechanics, the evidential situation is somewhat different. We can't directly observe the other branches of the wave function. If we could, they wouldn't be separate branches anymore. But we can test whether quantum mechanics itself is correct, and the many worlds interpretation is simply one way of understanding what quantum mechanics means. Every time we confirm a prediction of quantum mechanics, we're indirectly confirming the mathematics that many worlds take seriously. Proponents of many worlds argue that interference phenomena, like the famous double-slit experiment where particles seem to go through two slits at once, are best understood as showing us shadows of parallel reality. When an electron creates an interference pattern as if it went through both slits, many worlds says this is because versions of the electron in different branches of the wave function are interfering with each other before decoherence separates them completely. Critics counter that you can explain these phenomena without invoking parallel universes, using other interpretations of quantum mechanics. The debate here isn't really about empirical evidence in the usual sense. Everyone agrees on what experiments show. The dispute is about what the best interpretation of that evidence is, which gets into thornier questions about simplicity, elegance, and philosophical preference. String theory presents yet another evidential challenge. The theory itself makes predictions, but testing them is extraordinarily difficult, because the characteristic energy scale of string theory is so high. We'd need particle accelerators millions of times more powerful than anything we could realistically build. Some aspects of string theory might show up at energies we can access, like certain patterns in the masses and interactions of particles, but these tests are indirect and haven't yet yielded clear results. The landscape of string theory is even harder to test directly. If the landscape exists and if different universes in the multiverse correspond to different valleys in the landscape, we might be able to make statistical predictions similar to the anthropic arguments we discussed. But this requires understanding the landscape well enough to calculate what's typical and what's rare, which is an enormously difficult problem that physicists are still working on. Some researchers have proposed more exotic ways to search for multiverse evidence. If quantum mechanics allows for occasional weird fluctuations, maybe there's a tiny probability that we could detect a signal from another branch of the wave function, or that some particle could temporarily tunnel between universes. These ideas are highly speculative and push the boundaries of what's physically possible, but they show that scientists are thinking creatively about how to test ideas that seem fundamentally untestable. There's also the philosophical question of what counts as evidence. In science, we routinely accept the existence of things we can't directly observe. We believe in quarks even though we can't pull one out and examine it, because the theory of quarks makes successful predictions about things we can observe. We believe there are billions of galaxies beyond our cosmic horizon, even though we'll never see them, because the universe appears to be homogeneous and there's no reason to think it suddenly stops beyond what we can see. The multiverse might be similar. If our best theories, quantum mechanics, inflation, string theory, all point toward parallel universes as a natural consequence of their underlying mathematics,
Should we take that seriously even though we can't observe those universes directly? Or does the unobservability of other universes place them in a fundamentally different category from things like quarks or distant galaxies? These questions don't have easy answers. They get at deep issues about what science is, what counts as a scientific explanation, and how we should respond when our most successful theories seem to imply things that transcend direct empirical testing. Different scientists have different views on these matters, and the debate is ongoing and often heated. What we can say is this: if parallel universes exist, they're extraordinarily good at hiding from us. The universe we inhabit appears to be causally closed. We see no evidence of influence from outside, no windows into other realities, no messages from parallel worlds. If there are other universes out there, they're playing by rules that keep them completely separate from our own. That isolation is built into most multiverse theories. The other universes aren't just far away, they're fundamentally disconnected from ours in ways that make them unobservable in principle, not just in practice.
This puts the multiverse in a strange position scientifically. It emerges naturally from well-tested theories, yet it may never be directly confirmable. It might be one of those rare cases where we have strong theoretical reasons to believe something exists even though we know we can never point at it and say, there it is. Or it might turn out to be a beautiful mathematical artifact that doesn't correspond to physical reality. A case where we pushed our theories beyond their domain of validity and mistook mathematical possibility for physical fact. The search for evidence continues. New telescopes provide ever more detailed maps of the cosmic microwave background. Particle accelerators probe the frontiers of high-energy physics. Theoretical physicists refine their understanding of quantum mechanics, inflation, and string theory, looking for ways to make testable prediction. Maybe someday we'll find a smoking gun, some undeniable signature that can only be explained by the existence of parallel universes. Or maybe we'll find reasons to abandon the multiverse idea altogether. For now, we're left with intriguing possibilities and tantalizing clues, but nothing definitive. A situation that's both frustrating and appropriate for a question that probes the very limits of what we can know about reality. The question of whether parallel universes exist has sparked one of the most fascinating and sometimes contentious debates in modern physics. On one side stand physicists who see the multiverse as a natural and perhaps inevitable consequence of our best theory. On the other are skeptics who view it as speculative metaphysics dressed up as science. Let's explore the main arguments on both sides of this divide. The case for taking the multiverse seriously rests on several pillars. First is the sheer mathematical naturalness of multiverse scenario. Physicists didn't set out to invent parallel universes. They discovered them lurking in the equations of quantum mechanics, cosmic inflation, and string theory. When you take the wave function in quantum mechanics seriously and don't add in an extra collapse postulate, you get the many worlds interpretation. When you work out the details of cosmic inflation carefully, eternal inflation seems almost inevitable. When you explore the solutions to string theory, you find a vast landscape of possibilities. Supporters argue that we should pay attention when multiple independent theoretical frameworks all point in the same direction. It's like having different witnesses all giving the same testimony. None of them individually might be conclusive, but the convergence is suggestive. Maybe these theories are trying to tell us something important about how reality is structured. Another argument involves explanatory power. The multiverse offers potential explanations for puzzles that otherwise seem deeply mysterious. Why is the universe fine-tuned for life? In a multiverse, we just happen to inhabit one of the rare universes where the constants allow for complexity and observe. Why does quantum mechanics make probabilistic predictions? In many worlds, all outcomes occur, and probability reflects the relative weight of different branches. These aren't complete explanations, but they're frameworks that could potentially resolve long-standing mystery. Proponents also point to historical precedent. Science has repeatedly discovered that what we thought was everything is actually just a small part of something larger. Earth isn't the center of the universe, it's one planet among many. The sun isn't special, it's one star among billions. Our galaxy isn't the whole cosmos, it's one galaxy among countless others. The multiverse would be the latest in a long series of Copernican revolutions, expanding our perspective from the universe to our universe as just one among many. But the critics have powerful counter-arguments. The most fundamental objection is that the multiverse may not be science at all. Science, skeptics argue, is distinguished from other forms of inquiry by its commitment to empirical testability. If we can't observe other universes, if they're in principle forever beyond the reach of our instruments and experiments, then what does it mean to claim they exist? Aren't we just engaging in untestable speculation? This objection cuts deep because it challenges the scientific legitimacy of multiverse theories. Philosopher Karl Popper famously argued that scientific theories must be falsifiable. There must be some conceivable observation that could prove them wrong. If no observation could ever rule out the multiverse, is the idea even scientific? Some critics say no, arguing that multiverse theories have more in common with metaphysics or theology than with physics. Defenders respond that falsifiability is too strict a criteria. Many things in science aren't directly testable but are accepted because they're part of theories that do make testable predictions. We can't directly observe what happens inside a black hole, but we accept general relativity's description of black hole interiors, because general relativity has passed many other tests. Similarly, we might accept the multiverse if it's a natural consequence of theories that successfully predict things we can observe. Another objection involves Occam's razor and the principle of parsimony. Multiverse theories seem to multiply entities beyond necessity. Instead of one universe to explain, we now have infinitely many universes. How is that simpler? Critics argue that we should prefer theories that postulate the minimum number of unobservable entities, and a single universe is certainly simpler than countless parallel universes. Multiverse advocates counter that Occam's razor should be applied to the fundamental principles of a theory, not to how many entities it predicts. The many worlds interpretation, for instance, has simpler fundamental principles than the Copenhagen interpretation. It's just the Schrödinger equation with no added collapse postulate. The parallel universes aren't extra assumptions, they're consequences of taking the simple equations serious. Similarly, eternal inflation doesn't add extra complexity to inflation theory. It's what inflation naturally does when you include quantum effect. David Gross, a Nobel laureate and prominent critic of multiverse reasoning, has argued that anthropic explanations represent giving up on the goal of physics. Physics has always sought to explain why the universe has the properties it does, to find principles that determine the constants and laws we observe. The anthropic multiverse says, in effect, that there's no explanation. The constants are random, and we just got lucky. Gross sees this as abandoning the search for deeper understanding. Supporters like Leonard Susskind counter that we shouldn't let our preferences about what physics should be like override what our theories are telling us. If the landscape of string theory really contains 10 to the 500 different solutions,
We can't will that away just because we'd prefer a unique solution. And if most of those solutions correspond to universes that can't support life, then anthropic reasoning is a necessary tool for understanding why we observe the particular physics we do. The debate also touches on the sociology of science. Some critics worry that multiverse theories are too easy to hide behind. If a theoretical prediction doesn't match observation, you can always say that must be true in some other universe. This could make it harder to rule out wrong ideas and might lead physics down an unproductive. Others are concerned about the level of speculation involved. String theory itself is unproven, and the landscape is a consequence of string theory's structure. Eternal inflation is an extrapolation from standard inflation theory into domains we can't observe. The many worlds interpretation is just one way to understand quantum mechanics. Stacking these speculative ideas on top of each other, assuming string theory is right and eternal inflation happens and the landscape is real, seems to some critics like building a house of cards.
Multiverse proponents acknowledge these concerns, but argue that theoretical physicists have always had to think about possibilities beyond what's immediately testable. Einstein developed general relativity through thought experiments and mathematical reasoning, not because he had direct access to black holes or the Big Bang. Sometimes theory runs ahead of experiment, and that's okay as long as we're clear about what's established and what's speculative. There's also disagreement about what the current evidence means. Supporters point to things like the successful anthropic prediction of the cosmological constant as evidence that multiverse reasoning works. Critics see the same history differently, noting that anthropic reasoning didn't predict any specific value until after we'd narrowed down the possibilities through other means, and that one semi-successful prediction doesn't validate a whole framework. Interestingly, both sides often agree on the importance of the question. Even critics acknowledge that if a multiverse exists, it would be one of the most profound discoveries in the history of science, radically changing our understanding of reality and our place within it. And supporters acknowledge the challenges and uncertainties, recognizing that the multiverse remains unproven and may always resist direct confirmation. What this debate reveals is a science in transition, grappling with theories that push the boundaries of what's traditionally been considered testable or scientific. It's a healthy debate, one that forces us to think carefully about the foundations of scientific reasoning and the limits of human knowledge. Whether the multiverse is real or not, the discussion around it has illuminated important questions about what science is and how it should operate when confronting the ultimate questions about existence. As we've journeyed through these various multiverse theories, from quantum branching to cosmic inflation to the string landscape, you might be feeling a bit overwhelmed, and that's entirely understandable. These ideas are strange, vast, and profoundly disorienting. They challenge our most basic assumptions about reality, identity, and the nature of existence itself. So let's take a step back and think about what it all means, not just scientifically but philosophically and perhaps even personally. If the multiverse is real in any of its various forms, the implications are staggering. Start with the most immediate. You're not alone. I don't mean that there's alien life out there among the stars, though that might be true too. I mean something more radical. If the many worlds interpretation is correct, there are countless versions of you existing right now in different branches of the wave function, each one experiencing a slightly or dramatically different reality. Some made different choices at crucial moments. Some encountered different opportunities or misfortunes. All of them are equally real. All of them feel just as alive and conscious as you do. This raises profound questions about identity. What does it mean to be you, If there are countless other versions of you scattered across the branches of reality, are you just one thread in a vast ride of possibilities? When you make a choice, do you somehow split into multiple beings, each following a different path? Or are all these versions of you that exist in parallel better understood as different people who merely share a common past up to some branching point? Philosophers have grappled with such questions for centuries in thought experiments, but the many worlds interpretation suggests they might not be merely hypothetical. These questions might be about actual physical facts about how reality works. That's both thrilling and somewhat disturbing. It means the road not taken isn't just a metaphor. It's an actual path that an actual version of you is walking in another branch of the universe. The multiverse also raises questions about meaning and significance. We're used to thinking of our universe as everything that exists, as the whole stage on which the drama of existence plays out. If it's just one universe among countless others, does that make everything that happens here less significant? If there are infinite versions of Earth where every possible history plays out, does anything we do really matter? Different people will answer this question different. Some might feel diminished by the multiverse, finding it existentially troubling to imagine that everything we've ever done or experienced is replicated with variations in countless other realities. Others might find it liberating, a release from the pressure of thinking that this universe, this life, this moment is the only one there is or could be. But perhaps the multiverse doesn't diminish significance at all. Each universe, each branch, each bubble still exists. The experiences that occur in them are still real. The joy and suffering, the achievements and failures, the love and loss, all of it still matters to the beings experiencing it. If anything, the multiverse might multiply significance rather than diluting it, suggesting that reality is far richer and more abundant than a single universe could ever be. The fine-tuning problem takes on a different character in a multiverse context. Instead of wondering why the universe seems designed for life, we can understand it as an example of selection bias. But this doesn't entirely resolve the deeper question of why anything exists at all, or why the multiverse has the particular character it does. You can always ask why these laws of physics that allow for multiple universes, why this particular landscape of possibilities rather than some other landscape or no landscape at all. The multiverse, in other words, doesn't answer the ultimate metaphysical questions. It relocates. Instead of asking why the universe exists, we ask why the multiverse exists. Instead of asking why our universe has the properties it does, we ask why the multiverse generates universes with various properties according to certain distribution. These might be easier questions to approach scientifically, but they're not fundamentally different in kind from the questions they replace. Then there's the question of what counts as knowledge. One of the remarkable things about modern science is how much it's revealed about aspects of reality that seemed forever beyond human reach. We've figured out what stars are made of, what happened in the first moments after the Big Bang, what the internal structure of atoms looks like. We've developed theories that make astonishingly precise predictions about phenomena we can't directly observe. But the multiverse might represent a boundary beyond which knowledge becomes impossible in principle, not just in practice. If other universes are truly causally disconnected from ours, if there's no way for information to travel between them, then we might never be able to know for certain whether they exist. We can have theoretical reasons to believe in them, but we can't point to them and say there they are. This raises a philosophical question. What does it mean to know something you can't empirically verify? Is it enough to have a beautiful mathematically consistent theory that makes successful predictions about things you can observe, even if that theory also predicts things you can't observe?
Or does genuine knowledge require direct empirical confirmation? Different people will draw this line in different places. Some are comfortable extending the concept of knowledge to include well-grounded theoretical inference, even when direct observation is impossible. Others insist that science must always maintain a connection to the empirical, that theories without testable predictions aren't truly scientific. This is ultimately a question about the philosophy of science, about what distinguishes scientific knowledge from other forms of understanding. There's also something humbling about confronting the possibility of a multiverse. For all our technological and scientific achievements, for all we've learned about atoms and stars and the structure of space-time, we might be fundamentally limited in our ability to comprehend the full scope of reality. If there are other universes beyond our cosmic horizon, forever inaccessible to our observations and experiments, then the totality of existence might be far vaster and stranger than we can ever hope to fully understand. This limitation isn't necessarily a bad thing. It reminds us that there will always be mystery, always be questions at the frontier of human knowledge. The universe or multiverse might be inexhaustible in its depth and complexity, offering an endless source of wonder and inspiration for future generations to contemplate. At the same time, the fact that we can even conceive of these ideas, that we can use mathematics and logical reasoning to explore possibilities that might lie forever beyond direct observation, speaks to something remarkable about human consciousness and intelligence. We're pattern finders, theory builders, creatures who can imagine possibilities beyond our immediate experience. The multiverse theories, whether ultimately right or wrong, demonstrate the power of human thought to transcend the limits of direct perception. Perhaps what the multiverse debate reveals most clearly is that we're living at an extraordinary moment in the history of human understanding. We've developed theories so powerful and successful that they're making predictions that might transcend the possibility of empirical verification. We're confronting questions about the nature of reality that blur the boundaries between physics, philosophy, and metaphysics. And we're doing so with a mixture of rigorous mathematics, careful observation, and imaginative speculation. Whether parallel universes exist or not, the journey of exploring the question has revealed profound truths about the nature of science, the limits of knowledge, and the human capacity for wonder. It's reminded us that reality might be far stranger than common sense suggests, that the cosmos might be infinitely creative in ways we're only beginning to glimpse, and that some of the deepest questions we can ask might never have simple, definitive answers. In the end, perhaps what matters most isn't whether we can prove the multiverse exists, but what the possibility of parallel universes teaches us about how to approach the fundamental mysteries of existence with humility, imagination, and an openness to possibilities that challenge our assumptions about reality itself. And so we come to the end of our journey through the landscape of parallel universes, having explored quantum branching, cosmic inflation, string theory landscapes, fine-tuning mysteries, and the ongoing debate about what it all means. We've seen how multiple independent lines of reasoning in modern physics all seem to point towards some form of multiverse. The many worlds interpretation emerges from taking quantum mechanics seriously, without adding extra assumption. Eternal inflation arises naturally from our best understanding of the universe's earliest moments. The string landscape appears when we explore the possible solutions to string theory, and the fine-tuning of fundamental constants provides a compelling motivation for thinking there might be many universes with different properties. Yet we've also seen the challenges and uncertainties. We have no direct evidence for parallel universes. We might never be able to observe. Some scientists question whether the multiverse is even a scientific idea or merely metaphysical speculation. The debate continues, passionate and unresolved. What can we conclude? Perhaps simply this: reality might be far stranger and more vast than we ever imagined. The universe we can see, for all its grandeur, with its hundreds of billions of galaxies, its trillions upon trillions of stars, its unfathomable spans of space and time, might be just one small corner of something incomprehensibly large, or it might be all there is, unique and special in its existence. We don't know, and there's something beautiful about that uncertainty, about standing at the frontier of human knowledge and peering into possibilities that might forever remain just beyond our. It reminds us that mystery persists, that wonder endures, that the cosmos still has secrets it may never fully reveal. Whether you find the idea of parallel universes exciting or unsettling, probable or implausible, it's worth contemplating what these theories say about the human spirit. We're creatures who can conceive of possibilities beyond the visible universe, who can use mathematics and logic to explore realities we might never directly observe, who can ask questions about the nature of existence itself. That capacity for imagination and inquiry is itself remarkable, perhaps as extraordinary in its way as any multiverse could be. So as you drift off to sleep tonight, let your mind wander among these possibilities. Think of quantum branches splitting with every moment, of bubble universes forming in an eternally inflating background, of countless valleys in the string landscape, each hosting its own unique reality. Think of the fine-tuned constants that make our universe suitable for life, and ponder whether that reflects design, chance, or selection bias across a vast multiverse. And remember that whatever the ultimate truth about parallel universes, you're here, now, in this reality, experiencing this moment. That's something certain, something real, something worth cherishing. The mysteries remain, the questions endure, and the cosmos continues to inspire us with its depth and complexity. If you enjoyed this journey through the science and speculations surrounding parallel universes, please like this video and subscribe to Science Lullaby for more explorations of the cosmos. Share your thoughts in the comments. Do you think parallel universes exist? Which multiverse theory do you find most compelling? Until next time, sleep well, dream deeply, and keep wondering about the magnificent mysteries of existence. Sweet dreams, fellow travelers in this strange and beautiful cosmos.